Quantum computers are fast, but how fast are they? In particular, can they break the speed of information? In this video, I will tell you two things. First of all, what is the speed of information? And second, can quantum computers break it? And to illustrate this, we'll use a very famous quantum computing algorithm called Deutsch algorithm. So first of all, what is the speed limit of the universe? Well, we all know it's the speed of light, which is 300,000 kilometers per second. Now, information also has its own speed limit, and that is the logarithm base 2. Don't get scared of the word logarithm. What I really mean is 1 bit, 1 question. That means if you want to gain 1 bit of information, you need at the very least 1 yes/no question. Or the most you can gain with a yes/no question is 1 bit of information. Let's look at an example. So let's say that I have selected a number between 1 and 8, and you want to guess it using only yes/no questions. So you can start, for example, asking me if it's 1, and I say no. So you discard the 1, and then you ask, well, if it's 2, and I say no, so you discard the 2, and then you keep going with 3 and 4 until you say, is it 5? And it turns out I said yes, because it was 5. So you found it using 5 questions. Now the idea is to do this in as few questions as possible. Now that's not a good worded question because you could have found it in 1 if it was 1 or in 2 if it was 2. So what I really mean is using this strategy on average, what is the number of questions needed? So if you run this strategy many times with different numbers that I pick, what is the average number of questions needed? And is there a strategy that gives us a minimum number of questions needed on average? So this strategy gives rise to this tree. The first question says if it's 1, if yes, then it's 1. If not, then you ask a second question, which is it 2? If it's 2, then you're done. If not, you ask if it's 3, and so on and so forth, all the way to is it 7? Now, if you ask if it's 7 and the answer is yes, then it's 7. If the answer is no, then it's 8. You don't actually need an 8th question. So let's look at the average number of questions. Now, we're assuming that every number has the same possibility to be picked by me, which is 1/8. So how many questions are used with every scenario? Well, 1 question if it's 1, 2 questions if it's 2, all the way to 7 questions if it's 7, and also 7 questions if it's 8. So since they all have the same probability, then the average number of questions is this sum divided by 8, which is 4.375. So this strategy gives you an average number of questions of 4.375. The question is, can we do better? And yes, we can do much better. So check out this other strategy called binary search. With binary search, you would ask the question, is it among the first half? So basically you're splitting them into 2 groups of 4, and you're asking me, is it on the first half? And I say, no, it's not on the first half. So you can discard 4 numbers already with 1 question. That's pretty good. Then you keep asking the same question. Is it among the first half of the ones that I still have? And that's splitting them like this. And I would say, yes, it actually is. So now you only have these 2 numbers. And then you ask the same question again. Is it among the first half now? And I say yes, because it's among the first half of 5, 6, which is 5. So the number is 5. And you guessed it using only 3 questions. And notice that there's no luck involved. No matter what you do, you would guess it using 3 questions. And so that's the average number of questions for this strategy. This binary search strategy gives rise to this other tree where you would first ask if it's on the first half. I could say yes or no, and then based on that, you would ask if it's among the first half of the remaining ones, and then you ask the same question again. And with 3 questions, you are able to find it. So in this case, is it among the first half? No, so you discard that whole part of the tree. Then is it among the first half now? Yes, so you discard this part. And then is it among the first half now? Then yes, so you discard this part now. So no matter what happens, this strategy always gives you 3 questions. So the average number of questions is 3. Why 3? Well, because 8 is 2 to the power of 3. I need to multiply a 2 3 times to get 8. Why? Because here I have 1, then times 2, and times 2. In other words, 3 is the logarithm base 2 of 8. And so that logarithm base 2 of the number of possibilities is the average number of questions if I use this better strategy. Now it turns out that that's the speed limit of information. That's the best we can do. No matter what we do, we need at least 3 questions on average. So let's recap. we had the exhaustive tree, which is not a very good strategy. The average is 4.375. We have binary search, which is much better. It gives you an average of 3. And any tree that you draw, any strategy that you draw, will have some average number of questions that is bigger than or equal to 3. This is the best you can do. The best you can do is logarithm base 2 of the number of possibilities, which in this case is 3. Now, if you had, for example, to choose a number between 1 and 64, this would be the tree, where you would be asking every time, is it among the first half, or is it among the first half, etc., etc. And the average number of questions is 6 because 64 is 2 to the 6, or equivalently, the logarithm base 2 of 64 is 6. That's the number of questions, and that's actually the speed limit of information. The speed limit of information tells you 6 is the best you can do. So to clarify, why base 2? Well, because 6 questions means I multiply a 2 by itself 6 times to get the number of possibilities, which is 64. So in general, k questions gets you to guess 2 to the k possibilities, or if I have n possibilities, I need logarithm base 2 of n questions at least. Now, this is in a good case. My data could be disorganized and maybe I need more questions than that. But in an optimal case, the optimal strategy hits logarithm base 2 of n questions. Now, why am I saying it's a lower bound and not exact? Because when I have a number that is not a power of 2, for example, let's say I'm guessing a number between 1 and 50, well, the average number of questions, it's going to be bounded below by the logarithm base 2 of 50, which is 5.64 something, 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 because I'm not able to build that perfect tree. I fall short over here. And so we say that the average number of questions, which sometimes is going to be 5, sometimes is going to be 6, is going to amount to some number that's bigger than or equal to the logarithm base 2 of 50. If you're curious, it's actually strictly bigger because this number is irrational and the average number of questions in this optimal case is a rational number. And so that's why I'm saying that the speed limit of information is logarithm base 2 of n. Another way of seeing it is 1 bit, 1 question. If you ask one yes/no question, the best you can do is split your number of possibilities in half. Or in other words, you gain 1 bit of information. So if you have to win n bits of information, you need at least n yes/no questions. Now, to clarify, these are yes/no questions. I could not ask a question that would give me more than 1 possibility. For example, if I ask, what digit is that? That gives me 10 possibilities. That's cheating. I can only ask questions that have 2 possible outcomes. And who do we owe this? This genius over here, Shannon. He was the one who figured out entropy and information gain. I'm not going to enter into many details, but I do have a video called Shannon, Entropy and Information Gain. Definitely take a look if you want to learn this in more detail. The link is in the description of the video. Now, if you're enjoying this video, please hit subscribe. That will really help me make more videos. And also consider joining the channel. My videos are always going to be free, but if you support me more by joining, you will get some really cool perks. For example, you can get early access to videos, or you can get Q&As with me where we can talk more about these type of topics. So let me recap a little bit. If I have 64 possibilities, for example, and I want to bring it down to 1 possibility using yes/no questions, the best I can do is 6 questions, if I'm lucky. I can't do it in less, on average, because the logarithm base 2 of 64 is 6. But now, here's a question for you. Let's say that I have some problem with 400 possibilities, and I want to bring them down to 25 possibilities. Now, the question here is, what is the minimum number of questions that I would need to go from 400 down to 25? Feel free to pause the video and think about this. And I'll tell you, the answer is, well, if everything works out my way, with 1 question, I can get down to 200, and with another one down to 100, and with another one down to 50, and with another one down to 25. So I would need at least 4 questions to get there. And I can write that 4 as the logarithm of 400, which is the first number, divided by 25, which is the last number. In this case, 400 divided by 25 is 16, so I get logarithm base 2 of 16, which is 4. So in general, if I have A possibilities and I want to bring it down to B possibilities, the minimum number of questions, or the speed limit of information, tells me that I need at least logarithm base 2 of A, the first number, divided by B, the second number. So now let's talk about what this speed limit means. Well, like in the universe, cars can go fast and spaceships can go much faster, but nothing can go faster than the speed of light. The speed of light is the speed limit of the universe, which is 300,000 kilometers per second. Nothing can go faster than that. Well, with the speed of information, we have computers that are really fast. We have quantum computers, which are much faster, but nothing can go faster. That's the speed of information. So even quantum computers have to abide by this logarithm of 2 rule. That means no matter how amazing this quantum computer is, you can build a quantum computer using every single atom in the known universe, and it still has to abide by this speed limit. In other words, it needs one yes-no question to gain one bit of information. So then, why do we need quantum computers? Well, because many times they get much closer to the speed limit of information than classical computers do. There are problems for which a classical computer doesn't even get close to the speed of information, and the quantum computer actually hits it or gets closer. So here are some of the most famous quantum computing algorithms. We're going to see some of them over the next few videos. And notice that some of them actually do meet the speed limit, and some of them don't, but they get closer. So for example, Deutsch algorithm, which is the one that we're going to talk about today, does manage to hit the speed limit. Whereas Grover's algorithm, the speed limit is logarithm, and the classical computer does it in big O of n, and the quantum computer does it in big O of square root n. So it got better, but not yet hit the limit. So let's talk a little bit about Deutsch algorithm, but I want to make a small change. We've been talking about yes-no questions, but let's switch to yes-no observations. So observations that are binary observations means they have two outcomes, but they can be looking at something, hearing something, touching something, anything like that. But I emphasize, there can only be two outcomes. Looking at a dice is not a binary outcome, because by looking at it, I gain a lot more information. I can gain a number from 1 to 6. Looking at a digit is also not a binary observation, because I can gain information about a number being one of 10 possibilities. So only things like looking at a coin flip, or hearing a click or no click, or sensing something to be hot or cold, or basically anything that has only two outcomes is a binary observation. And I want to show you next is that even humans have to abide by the speed of information. And sometimes it's easy to hit the speed of information, but there are some cases where it's hard or even impossible to reach the speed of information, and we have to do more observations that we would actually hypothetically need. So to get to one of those problems, let's start with something easy. Let's say I have a coin that could be heads or tails, and I toss the coin and I don't know what it is yet. So if I want to find out if it's heads or tails, how many binary observations do I need? Well, I need one. I need to look at the coin and see that, for example, it's heads. That's one observation, and it took me from two outcomes to one, so the speed limit says that I needed one observation. So that's no problem. Now let's do another slightly harder problem, but still easy. We have now two coins. They could be heads or tails, and I want to find out if they're heads heads, heads tails, tails heads, or tails tails. How many observations do I need? Well, I need to at least look at the first coin to see if it's heads, and look at the second coin to see that it's tails, and two observations did the job. Now, why is that the speed limit? Because we went from 4 possibilities with one observation, we went down to 2 possibilities. When looking at the first coin, we found out that it's heads, so now there's 2 possibilities, heads, heads, or heads, tails. And we need another observation, which is looking at the second coin to get from heads, heads, head, tails to head tails, because we looked at the second coin. And that's the speed limit, because the logarithm of 4, the first number, divided by 1 is equal to 2. So we managed to hit the speed limit. But as I said, this is not always the case. Sometimes problems get harder. Here is a problem where the speed limit is harder to reach. Let's say I still have 2 coins, and I don't know what they are, but I don't want to find out what they are. The question I have is, do they show the same outcome? So did they both fall on the same face, whether it's heads heads or tails tails, or did they fall on different outcomes? So how would you find out if they're the same or different? Well, one way is to look at the first coin and get, for example, heads, and then to look at the second coin and get, for example, tails, and then compare them in our head and conclude that they're different. So that took 2 observations. However, that's not the speed limit, because the speed limit says if you want to go down from 4 observations all the way down to 2 observations, you really need just one yes-no question, which is, are they the same or different? You only need to bring it down to 2 observations, not to 1. You don't need to know if it's heads heads or tails tails. You need to know if they're the same or if they're different. You're going from 4 possibilities down to 2 possibilities. And 4 divided by 2 is 2, and the logarithm base 2 of 2 is 1. So the speed limit says you can't do it in less than one observation, but we did 2 observations. Now the question is this speed limit reachable? And I want to encourage you to think about it. So if you want to pause the video and think about how would you design an experiment where you could flip 2 coins and with one observation be able to find out if they're showing the same face or different face. And the hint is we may need to go to a different sense. We may not be able to get this by looking, but by hearing. So let's imagine this experiment. We have the coins and we put them over a table and we put them inside a box so we can't look at them, but however, we can manipulate them a little bit. So let's say that for our coins, we actually pick magnets, and these magnets have the head side is positive and the tail side is negative. So this is how they look. Now, if I manage to stick a piece of paper underneath the box and lift one of the coins and put it on top of the other one, then 2 things can happen. They can attract or they can repel. In this case, they repel because they have a positive on the bottom side of the top one and a positive on the top side of the bottom one, so they will repel. But they would attract if they have the same face. So let's look at the 4 cases. We have heads, heads, that's case 1, then heads, tails, case 2, tails, heads, that's case 3, and tails, tails, which is case 4. And here are their magnetic poles, and notice that when they are the same, they have different magnetic poles, so they attract, and when they're different, they have the same magnetic pole, so they repel. So now all we have to do is, without looking, we just listen, and if we hear a click, it means the coins had the same face. And if we didn't hear a click, it means they had different faces. So with one binary observation, this time being hearing, we managed to find out if they fall in the same face or in different. And actually, that's what the speed limit of information tells us. So with a little bit of twisting things around, we were able to hit the speed limit of information. Now, what does that have to do with quantum and classical computers? Well, a classical computer can only see. In other words, if the classical computer wants to know if 2 coins are both heads or both tails, it has to get its magnifying glass and then look at the first one and then look at the second one and then in its head compare if they're the same. So it needs 2 observations no matter what. Even if we get clever, if we say, hey, let's call the heads 0 and the tails 1, and we add them and only look at the outcomes parity, and if it's 0, then they're equal, and if it's 1, then they're different. Yes, sure, but for the computer to be able to do the sum, it needs to observe the 2 variables. So it needs to look at the first one and look at the second one. So the classical computer needs to observe both. On the other hand, the quantum computer actually can hear, actually can manipulate things and play that other experiment where it's able to put them in a box and with one observation be able to hear the magnetic click or no magnetic click. So it doesn't see, it instead puts a stethoscope and listens inside the box. Now, if I were to ask the quantum computer, are they heads heads or tails tails? The computer would say, I have no idea, because for that, I would need another observation. If I were to know, then I would be surpassing the speed of information. I can't do that. I can only tell you if they're the same or if they're different because I used one observation. So obviously there's a lot more to this because the computer's not looking or hearing. They're actually just applying algebraic manipulations to either bits or qubits. And I'm going to tell you all these details in the next video, which is the Deutsch-Josa algorithm. It's a beautiful, beautiful algorithm that encompasses wonderful things that you can do with a quantum computer. But for now, I want you to remember one thing. A quantum computer is not a really fast classical computer, because the classical computer, no matter what, needs to make the 2 observations, whereas the quantum computer can make one observation because it can manipulate the things without looking at them. Now, we have very fast classical computers that make those 2 observations really, really fast, so it looks like it did it in a heartbeat, but it always has to do the 2 observations. So one of the main differences between classical computers and quantum computers is that when the classical computers want to do a calculation, it has to observe all the variables first. On the other hand, the classical computer can manipulate variables without observing them and then observing at the very end. That's one of the very special things of a quantum computer. So I'll give you a perhaps oversimplified example, but just to give you the idea. Let's say you have a 0 and a 1, and you want to apply a function to them. Well, the classical computer has to apply it to 0 and to 1. And let's say applying that function is really expensive, so we want to apply it less. Well, the quantum computer can actually make a superposition of the 0 and the 1 and then apply the function to that. That's only one application of the function. And then later, it observes the answer. Now, this looks easy, but it's actually very hard. Manipulating these qubits is very tricky, not just physically, but also mathematically. And furthermore, a lot of information gets lost when you observe qubits. So it's not just magically you do a superposition and do all the calculations and then look at the one you want. No, these things can be pretty tricky. And that's why quantum algorithms are so fascinating. So in the next video, we're going to learn this in detail. What is a qubit? What is superposition? And how is it that we get the quantum computer to hear that click? So that's all for now. I want to thank my quantum genius friends. I could have not made this video if not for the help of these people who gave me a lot of feedback and a lot of ideas. And actually, throughout the years, I have learned from them and a lot of other people who have had lots of patience, because believe me, I ask a lot of questions, way more than the speed limit of information. So thank you to them and to all of those who have taught me quantum computing. And thanks to you as well for your attention. If you like this video, please subscribe to the channel. That will help me make a lot more videos. You can also support me on Patreon or follow me on Twitter, Serrano Academy, or check out my page, serrano.academy, or check out my book, Grokking Machine Learning. The links are all in the comments with a discount code. So thank you very much for your attention, and see you in the next video where we're going to learn Deutsch algorithm.